All right. Anyone have any ideas what's going on? Someone heard a good explanation? Raise your hand. Go ahead.
This is just like my guess, but I would say like the centrifugal force pushes the water towards the outside, and then like it just gets far enough out that.
Okay, so maybe like the centrifugal force is going to add some speed when it comes off, more than your speed at the bike, so it can come. Okay.
So the speed the bike's moving will be the speed that the center point of the wheel will be, but the points on the outside of the wheel will be faster than the points closest to the center.
Wait, but if all the points are moving faster than the center point, then my wheel better be way ahead of me as soon as I start going, right?
Well, no, the center is the same speed as the bike. But as you get farther out, those points are moving faster relative to the center. And so the water, when it hits the wheel, is moving faster relative to you.
But still, like there's always water maybe on the bottom of my tire, and if that's moving faster relative to me, that ought to be moving down the road faster.
I think so, I like that. But you're also moving faster than people down the road.
Yeah, so where's over here, Christian?
The way I thought about it is the only way you would be able to get up to your back is if, because the reason it would stay in like this, like not get to your back is because of the wind, but there's like a low pressure zone right behind your back.
Oh, so you think, okay, so you're thinking like, is it some sort of vacuum thing happening so that the air resistance is minimal, okay? All right?
So your reference frame is wrong. You want to
Okay, so here's the physicist.
okay.
Because physicists, when you say how fast, when you talk about how fast, they will say what? They'll say relative to what? Okay, so go ahead.
So you want to be relative to where the tire is contact. Because at that point, the velocity is zero. So where you're actually picking up the rate droplet, it's moving at zero velocity and then gets pushed forward rather than back. And so it's actually just a sine or cosine function where it slowly speeds up as it goes up and it's constantly moving.
Okay, so it's not exactly sine or cosine, it doesn't constantly move forward, but in general you're right. Like there's something happening. I said that, you know, and you were also right around where we're going to with your explanation. So the tire on average is moving the same speed as the bike, but the top of the tire is actually moving faster than the points on the bottom of the tire. That might sound really weird. Relative to the ground. So, let's say here's a point and here's a point, and then I roll that. I'm going to roll that wheel a little bit. Where do those points end up? So that point went like this. This point went like that. Okay? If you were on the edge of a wheel, on the bike that you were going down the street, it wouldn't feel like you're on a merry-go-round. You would feel like you get whipped up and down. Boom, 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 as the bike was going. Right? That's what happens to the points on the wheel. So they follow a path. If we continue this down to where this started and down over here, they follow a path. You guys know the path that's called? Cycloid. Okay? They follow a cycloidal path. Okay? Cycloids are pretty cool. It shared some information about a cycloid in your in the reading. So here I have a ramp. Sorry for those that just get to watch the recording. You'll have to Google this or something. Find animations with it where this happens. But here I've got two ramps. Okay, I've got the straight linear ramp, and I've got this. It's a cycloidal ramp. I've got two golf balls. I'm going to roll them down, one in each of the ramps. The question is, which ramp will get the ball here first? So talk to your neighbor. 10 seconds. Okay, so we three options. You could say the linear one, you could say the cycloidal one, or you could say about the same. Okay, so we're going to do a quick snap survey. So snap if you think the top one's going to get there first. Snap if you think the cycloidal one will get there first. Snap if you think they're going to be about the same. Okay, so not a lot for the first takers. So going to come grab these. And my last class. Sure. Yeah, move out of the way. Move to the side. Yeah, there. Okay. My last class, the guy that I got to catch didn't catch either one. So ready? Thank you. So none of the above. Okay. I didn't push it down, I promise. Here, watch it. Okay, ready? Okay. So cycloid is much faster. And in fact, the cycloid is the fastest path. If you give 2 points, one below the other one, and you want to know the path of the ramp for a rolling ball to get to just by its own weight, the path is a portion of the cycloid. Okay. Now that's pretty cool, but that's not amazing. But this is amazing. No matter where you start the ball, as long as you don't start at the bottom, it takes the exact same amount of time for the ball to roll down to the bottom, just like that. So there's a mark here. I don't have it's not a very big mark, but it's right here. I'll put this near right near the bottom. No matter where you start it, it takes the same amount of time to get down to the ball. That is phenomenal. If I were to have asked you before, could you make a ramp so that no matter where you started the ball, it would hit the bottom at the same time? How many of you would say that's impossible? I mean, be honest. You think like that's it's not impossible. You're right. So, the cycloid has some other amazing properties. It turns out to minimize a lot of cool things. And it actually, the people early on that developed the cycloid, it turned into its own field of calculus called the calculus of variations that gives you up that helps you to minimize and maximize things. So, another really cool thing about the cycloid before we move on, if you take two pieces of cycloid, and then you take a pendulum, and you drop the pendulum down, and if the pendulum rope is the same length as, that would allow you to go halfway around the cycloid, and then you start to swing that pendulum so that it would wrap around. So if it wrap around and then go straight. Then, no matter how far it swings back and forth, how big the swing is, it takes exactly the same amount of time to go back and forth. Now, you guys already thought that was true for any pendulum. It's not true. The smaller the swing back and forth, the closer it is. But here you can actually swing it quite big. And here it can actually be slowing down. You can start it up high, and it'll slow down, and it still takes the same, or very close to the same amount of time to swing back and forth. So you can make a much more accurate pendulum clock with this, which is what they did. Yes? Yeah, so you have to think about two cycloidal barriers, okay? So these are all right, so these are like pieces of wood that are carved out. And so that as you swing the pendulum back and forth, then it's getting wrapped around here. So the pendulum, when it's all the way to the top, here, it's going to be wrapped around, and then as it falls down, oops, it's not quite like that, it'll unwrap. So, and the path it takes is actually another cycloid. So, all right, let's get back to our problem. So why are we talking about this with this section? Because that piece of mud is taking the path of a cycloid, and the cycloid is easily derived in terms of a parametric equation, not so easily with x in terms of y. It's really, really ugly, actually, if you do it in terms of x in terms of y. You get inverse cosine and all sorts of stuff. But if you take x of theta, you get r times theta minus sine of theta, and y of theta is r times 1 minus cosine of theta. And they do derive it in the book. I can do it really fast. So it doesn't look like voodoo to you. So if this is where we started, so if this point started over here, we rolled it up, then, and this was the origin right there, then we need to figure out the x coordinate and the y coordinate of that, and given our angle theta there. Well, our x coordinate is this total distance minus this distance. Well, this distance that we're going to subtract is the same as this. And if this distance is the radius, what is this distance? It's our sine of theta. What is this total distance here? Well, the total distance there is how far the ball is rolled, which is this distance along that curve, which is just r times theta. So theta is the number of radians to go around. You multiply that by how long the radius is. That tells you your distance. So now the x-coordinate will be this minus that, which is what we have, except we factored out an r. So r of theta minus r sine of theta. And the x-coordinate, the y-coordinate's even easier. So this distance is r. The y-coordinate is this distance, or this distance, or this distance. How do we find that? Well, we can calculate this distance, but that's just the length of this triangle, which is r cosine theta. So we just take r, this total distance r, minus r cosine theta. So r minus r cosine theta. So that's x at any theta. It's y at any theta. And that's what we have here, except we factor down an r. Okay? So your task. I've done enough talking today. Your task. You're driving your bike down the road at 5 meters per second. You're on a 700 millimeter bike, so the tires are 700 millimeters or 0.7 meters, okay, in diameter. And the question is, how fast, when the piece of mud is right here, how fast is it moving in the x direction? How fast is it moving in the y direction? And just how fast is it moving relative to the air around it, I guess. Okay. So how fast, we need something in terms of time. What we have set up here is in terms of angles. You'll have to do a little math to get the angles in terms of time. There are a couple different ways to do this, but let me turn you loose for a few minutes. See what you guys can come up with. Oh, you bet. So I'm working through it up here, but there's lots of different ways to attack this problem. Just because your work doesn't look like mine doesn't mean that you're doing it incorrectly. In fact, those of you that have had some physics probably have a much better way to attack this than me. So I've never had a physics class in my life. So, but I am using dimensional analysis here to help me out with the units. So. Okay, so let me explain a little bit about what I did. We have this problem where we know what our position is in terms of theta, but if we want to answer the question about how fast we're going, we need to know our position in terms of time. So I need to get something that connects our theta, like our angle measure, and time. So I take the speed of the bike here. I thought about how many times. So every second I go 5 meters. Well, how many rotations do I get every second? If I go 5 meters, well, it's divided by the circumference of the wheel. This is 0.7 meters times pi. So that tells me how many rotations I make every second. But for every rotation, I get 2 pi radians. So I have to multiply that by 2 pi. And the pi's cancel out, and I get 107 sevenths. So I know every second I get 107th radians. And so I can connect. I wrote that in this equation here. And then I just replaced, all I did was replace all my thetas with 100/7 times t. Now that's one strategy. We haven't quite got there, but to answer the first question about how fast is it going in terms of t, we could start, at how fast is it going right when that piece of mud is right there, then I could start by taking the derivative of x of t. I do have to know what time it is at that point. We'll do that in a second. There is another way. Did anyone do this with related rates? Okay, I'm surprised nobody screamed when I said related rates. The way that most kids have experienced is related rates in 112. But did anyone do related rates? Okay. So it's actually a little bit easier if you do it in terms of related rates. All you need is this equation. All you need is this equation, and you could actually just start taking the derivative up here. So doing it the related weights way, then we have x of theta equals 0.7 over 2 theta minus sine of theta. This looks a lot easier to take the derivative of. So we really want dx dt, but dx dt is dx d theta times d theta dt. D theta d, or theta with respect to t is just 100 over 7t. So d theta dt is going to be 100 over 7. So if we find dx d theta, that's going to be 0.7 over 2 times 1, or sorry, times, yeah, times 1 minus derivative of sine of theta, cosine of theta. I should do time, this is 1, well, never mind, let's keep it at 1. And what's d theta dt we already solved for here, we just have to multiply those together. So 0.7 over 2, 1 minus cosine of theta, times 100 over 7. And what theta do we care about? Pi halves. We want to know how fast is that thing going in the x direction. 1 theta is pi halves. So you can plug in pi halves. We get 0.72, 1 minus, what's cosine at pi halves? 0 times 100 over 7. This piece is 0. So you end up with 0.7 over 2 times 100 over 7. And 2 will go into 150 times. 0.7 over 7. That's the same as 1/10, so you get 50 over 10, which is 5 meters per second. So, some of you I know were able to reason through that at that point, the speed of that mud should be traveling in the x coordinate, the same speed as the bike, the same speed as the center of that tire. Okay, a small change is going to move it in the x direction about the same distance as the center of the tire. Okay, so that's how you do it the related rates way. If you put it in terms of t, we can just find dx dt directly here. So 100 over 7 minus, derivative sine is cosine. We do have to do chain rule. Times 100 over 7. Okay. There. And that looks, the only difference from our related rates way is here we had the 107ths on the outside. So we've written it on the inside the other way. And instead of cosine of pi halves, we have, instead of cosine of theta, we have cosine in terms of t. So what we have to do is we have to find out when is t, for what value of t does theta equal pi halves. And that we can find using this equation here. T, you solve, you divide by 100, so you get 200, multiply by 7, so you get 7 pi. So t at 7 pi over 200. So you have to plug that in. So it turns out to be about 1/10 of a second. You punch it out, about 0.11 of a second. So you punch that out. You actually don't have to punch it out on your calculator because things simplify out, and you just end up finding the cosine of 100 over 7, the cosine of 100 over 7 times 7 pi over 200, which is just pi halves. So you get cosine of pi halves, which is what we found before. The whole thing simplifies to 5 meters per second. So we just did the same thing, just 2 different ways. So here you have to evaluate it at t equals 7 pi over 200. So you mean inside right there? Yeah. Well, this one, the 107ths, have already been multiplied in, whereas we had a 1 on this other one, but the 107ths was on the outside. And once we multiply it in, you get a 107ths here and a 107ths times. Yeah. So it was just factored out in this one. So. All right. Now, after this question, I'm going to treat you guys loose. You guys tell me how fast it's going in the y direction. Yes. Yep. Doing all my physics stuff here. Yeah. Okay, so see if you guys can find the speed that it's going in the y direction at that moment. Okay. Y of theta was R1 minus cosine of theta. So okay, I actually just looked at the time. We better not take time to do that right now. Anyone have any guesses? It's actually also moving 5 meters per second. So, so right at that point, as that mud comes off, which direction is it heading? Talk to your neighbor, okay, and tell your neighbor which direction. You do it with an angle with your hand. Which direction do you think that it's coming? If it flies off the bike, you're going forward. The wheel comes up. You're right here, right on the edge of that wheel, and it comes off the wheel. What's going to happen? All right. I'm going to ask. Okay, we're going to take a little poll. Everyone just put their hand up, their arm up at the direction you think it's going to go. We'll just do it relative to this bike going this way. Okay? So go ahead right now. Lift up your arm. Where's it going? Okay. So lots of dabs. Is that what that's called? Okay. And lots of straight ups. Okay. No one's going this way. That's good. Okay. So someone that went straight up, tell me. Like I know your whole group over there was going straight up, Kristen. That's a good direction to go. You don't want to head up. You know, up the ladder of success. What are you guys thinking? Yes. So like. Okay, we'll talk about why you think you'd be a mistake.
So we're talking about like the
The X and Y direct. X, Y,
now I would.
Okay.
Because
Okay, so we did take measurements. Well, I actually told you guys didn't have a chance to figure it out, but dx dt and dy dt were the same. They're 5 meters a second. So what's dy dx? Yep, it's dy dt, oops, over dx dt, which is going to be 5 over 5, 1. So the slope, dy dx is 1. The slope is 1. It's going to go in 45 at a 45 degree angle this way. And in fact, the piece of mud is always traveling on the way up. It's always traveling directly towards the top of the tire. Interestingly, it's always, no matter where you're at, the direction it's heading. If the tire were to stop and the mud come off, it would be heading right towards the tire. Right, but not just at that point. Even if it was right there, it would be heading right in this direction towards the top of the tire. Even if it was right here, it would be going in this, that direction towards the top of the tire. Side note about cycloids. Yes. The piece of mud is going down. I don't know about that, because the piece of mud. So if it's right here, I think it's always heading away from the top of the tire. So because the bottom of the tire is back, the bottom of the tire is back here, it's not going to be moving back, but it's always heading away from. So good thing. All right. So so we won't be able to answer the real question we wanted to know, which is how fast you can ride your bike without it flipping up on the back of your tire. To do it, we actually parameterize another curve, which is right when the tire leaves, then it becomes a ballistic equation, right? It's a kinematics, whatever you call it, right? You're going to use gravity in the y direction and constant speed, the speed it leaves in the x direction, and now you have a different path you care about. And you also have to think about the path of your backside as it's moving along, and you have to figure out when it might intersect. We're not going to take time to do that. It turns out to be about 8.5 miles an hour, if I remember right, when I did this several months ago. Yeah, it's just an RU here, please. Still going, huh? So you can. Okay. Someone asked about what happens when you run, like flipping water up on your legs. That is a good question. We don't. Let me talk about. I forgot to talk. How fast? We never talked about the total speed. How fast is it going? How fast is it going when it leaves right here? We talked about the direction. How fast is it going? Oh, horrible handwriting. I know some of you got to this in lab yesterday. So this would be the speed right there. And in general, the speed at any point, dx dt squared plus dy dt squared. This will be your velocity. Okay? And that looks very similar to something you read about in the book. What does that look similar to? Arc length. It looks similar to the arc length, except we don't have a formula just like this. We don't have an expression. What do we have to do to calculate arc length? We have to integrate it. So if you know your velocity at any moment, and you take that moment for a small period of time, you get distance, right? And if you keep doing that, then you have a different velocity for the next period of time, a different velocity for the next period of time. If you take those products and you add them together, then you get a total distance. That's what arc length is a total distance of something that's traveled. Or at least in terms of parametric equations, you think of it as in terms of something. So here we have the velocity. Here's the velocity here, and you have times a small time to get your distance. Okay. We haven't had time to do an area formula, an area problem. So usually we would like to, we're used to doing functions of x times dx to get areas. That still works in some sense. That still works on an xy plane. We draw these parameterized curves on an xy plane. The rectangles that we want still have lengths in terms of x and y. But what is this length right there? If this is a parameterized curve, say at t equals a, what is this length? Y of what? Yeah, y of whatever t is, in this case a. So that gives me a height. I have to multiply it by this length. What's that length? But the problem is if we do this a lot, you're saying the heights are in terms of t's. So it doesn't, if I have heights in terms of t's, I'm not going to be integrating with respect to x. So I somehow need to make this dx down here, I need to make it in terms of t. What's dx in terms of t? T or dt. So, oops. If I take dx dt and multiply by dt, I get dx. So I can replace dx with this. So I can't. So this dx I can change, or to x prime of t dt. I don't know what I did there. Okay. All right. Sorry we haven't had a chance to do examples of that. But have a great day. Have a great weekend. One more week. Final exams a week from tomorrow. Study hard.